Welcome. Let's talk about identifying code smells, at least a few of them. Very short introduction on my part. My name is Arne Mertz. I work at Zühlke Engineering as a software engineer, mostly in embedded parts. Have been using or trying to learn C++ for almost 2 decades. As most of you know, you never stop learning C++, right? And I've been a trainer for C++ for maintainable code, refactoring, testing, that kind of stuff, internally and also externally for a couple of years now. So yeah, so much about me. Let's talk about code smells. What are code smells? So this is a quote by Martin Fowler, that code smell, or a code smell, is a surface indication that usually corresponds to a deeper problem in the system. And there are basically 3 important parts in here. The first one is, it's a surface indication. So the code smell itself is not the actual problem in the code. So I think this is something to keep in mind when you see a code smell. We can't just say, hey, you have a problem in your code. We have to look deeper. So, but with the surface indication, meaning those are things that usually are relatively easy to spot. So you have something that you see, where you can see, okay, there might be a problem behind this. So you have a trigger to investigate whether there actually is a problem behind the indication you see. The second one is the actual deeper problem. Usually those are violation of programming principles, like the solid principles, or KISS principle, Jagdweg principle. We'll go into a few of those a bit later. And usually those problems or this violation of principle means that we are missing some patterns, we are missing abstractions, and we are lacking things that would make our code more maintainable, more readable, more understandable, sometimes even more secure. So by getting rid of those problems, we sometimes see that we have actually a bug in our code base. And the important part is that those surface indications usually correspond to deeper problems, not always. So there may be cases where you see like, oh, this looks not right, we should use something else, maybe, but if you dig deeper into it, then you see that, well, this is a corner case where we actually need to leave the code smell in the code, at least for now. And we will see an instant of when this usually actually is not a problem, or fixing the problem would actually make it worse later. I'll be presenting a couple of code snippets from open source code bases on GitHub. I really want to stress that this is not about picking on those code bases, not saying like those code bases are really bad. It's not picking on the developers. It's just to give you examples of instances of those code smells. Sometimes, or in many of the cases, there actually are violations of principles. That does not mean that those code bases are really bad code bases, right? So this is something that always, or very often happens while we are developing code. We are growing our code bases, and many of the things we will see just happen over time due to several reasons, because we lack the time to actually maintain and keep it really clean. So this is something that happens in any code base. Most of the snippets I will be showing are from the examples sections of those open source code bases. Meaning they're not actual production code. So if you're actually using those code bases, you won't have like these code smells in your code base as well. But on the other hand, example code should be maintainable, especially it should be readable, right? Because example code is meant for any of us to actually understand how to use a system, how to use a library, and how to actually use the code we see in the open source code bases. So getting rid of those code smells over there, making the code more readable, more maintainable, more understandable for us is actually maybe even more important than like making the code very clean in somewhere in the very deep recesses of the production code that we will never see and never touch. So the first example code is from SFML, which is the Simple and Fast Multimedia Library. And they have an example that is nowadays called tennis. Earlier it was called Pong. I mean, it looks pretty much like Pong, right? You have a pedal on the left side, you have a pedal on the right side, and there's this ball going in between those pedals. And the whole example is one long main function with a bit over 250 lines of code. So you may not be able to read the code that's actually on there. That's okay, because I will show you like smaller parts of this function. But what you may be seeing is that there's use of an SF vector, of SF windows, anything in the namespace SF is from this SFML library. So this example code base is meant to show how you can write a simple game using the SFML library. So the first code smell I'd like to talk about is long function. Maybe your ears picked up when you heard me mentioning those are 250 lines of code in one main function. Maybe 250 lines is a bit much, right? So this is something that is relatively common. So let me see a show of hands. What's the longest function you've ever seen? Anyone has seen a function over 1,000 lines of code? Okay. How about over 10,000 lines of codes? Great, still a few people. So you see, it's not that uncommon that we have long functions, right? So let me get a bit into later how long is too long, because it's not that easy. The deeper problem usually violated is that if you have a function that is that long, then we have the function usually is doing different kinds of things, a lot of different things. So this is a violation of the single responsibility principle, because a function should be responsible for one single thing. And another principle that is violated is a single level of abstraction, which usually means we have functions that work on a high level of abstraction, and we have functions that work on a low level of abstraction, and maybe some functions that work in between, so on different levels, but each function should work on one level only. So we don't want to have a function that has like, okay, I do some high-level function call here, and then I have like 50 lines of code that are really detailed bit shifting stuff on a very low level, and then I call another high-level function, right? So this would be a violation of a single level of abstraction. What you see here on the right is part of the, well, more first lines, formal lines in the function where objects are initialized for this game. So you see a rectangle shape that is the right pedal. So if you go back to the, let's see, if you can go back. So the right pedal, the red one on the side there. Then we see the ball is created. The left pedal is right above the slide, so it's coming immediately before this. Then there's a text font that gets loaded, and then there's a message for when you pause the game that has to be initialized, has to be set a font and a font size, and so on and so forth. So here we see something that is could be called a secondary indicator for this kind of long function, because what we very often have in these very long functions are these blocks of code where we have multiple lines and a comment before this block of code, what's going on in this block of code. these ones. So basically, this is a clear indication that this is actually already violating the single responsibility, right? Because this function has a responsibility of, among other things, creating the pedals, creating the balls, setting the fonts, initializing the pause messages, and later on in the function we have like the main loop of the game, and everything is inside one function. So back to how long is too long? Well, it depends on actually on the content of the function, right? So we have to analyze whether this function is doing more than one thing or whether it's violating the single level of abstraction. So here we see another example, which is example code from the Qt documentation, where we have a text edit field that's and a cursor, and then we have like a few frames and different text styles and character formats that will be used. And then the function starts using the cursor to insert different blocks and tables and writing text into a frame. And the function goes on for quite some time. So it's not the 250 lines of code, but I think it's about 100 lines of code. And it's using the cursor, the cursor, the cursor, the cursor, the cursor. And so this is something that, in my experience, you see relatively often in Qt, that you use something for quite, and you have to do quite a few function calls to get something done. To initialize a window, you have to create a window, then you have to set the border size, then you have to set the dimensions, you have to set some colors, you have to set this, you have to set that. So these functions tend to get relatively long while still using one thing. So in this example, I would say there are still a few couple of things that you could factor out, put into another function, because like doing the text frame format and then set a padding on the text frame format, like in the 5th to 6th lines and something like that. Those are tiny bits that could be factored out, but still the overall function will still have like a couple of lines of code, just because it's a relatively verbose framework in this case, in this use case. So you probably won't get this function below like 20, 30, 40 lines of code. So in this case, if you, for example, use a tool that says, I have a code smell here because you have a function that's longer than 20 lines of code, it's okay in this case. So you will get a warning for this function either way. But in some other case, you have a 15 line of code function where that actually is an instance of the long function smell. So there is no hard cut that you can use, right? And what I see relatively often is when people actually use metrics to find code smells or improvable code, they just said, okay, I have a limit, 20 lines of code, and then if I have a 40 line of code functions, they don't ask the question, is 40 line of code actually the correct length for this function? They just break it down into part 1, part 2, which is not the right way to do, right? And on the other hand, the 40-line function or the 30-line function still can be too long because it does too many things at once, right? So, but the tool won't trigger a warning, so they just leave it like that and it's okay. So those tools don't replace actual code reviews and seeing, is this function too long? And you get the same thing for other kinds of smells where you don't have like a definite number or a definite technically measurable indicator whether a code smell is there or is not there, or whether or more or less you see the code smell or you sniff the code smell, but you don't see if the actual underlying problem is there or not. So how do we fix the long function code smell? Usually it's relatively simple. We factor out functions of lower details and leave a function that has only higher function controls. So this is the shape update function. So this is actual production code in SFML again. So the shape is the base class of the rectangle shape and the circle shape we have seen for the game. And this update function first does a lot of lower detail stuff with the vertices, and so I used a little smaller font here because it's, well, the details of the first 15 lines of code or what it is are not too important, but it has to do, a lot with vertices and so on. And then it calls update fill colors, update text coordinates, update outline, which is relatively obviously a completely different level of abstraction, right? Than like the going through all the individual vertices on the shape. So judging from the comments above those 3 function calls on the bottom side of the function, there may be the people have been started to refactor this function to factor out actual functions for those blocks that were there before. Maybe they did it because they wanted to reuse this because, well, these update fill killers, update text coordinates are called elsewhere in the same file. But for example, this could be, I don't know whether it was an example where if you have a warning like 20 lines of code and more than 20 lines of code is too much, then you start refactoring, you factor out 3 functions, and now it's at 19 lines of code, it's okay. Maybe. I don't think so, but I tried to look into the history of this part of code, and I didn't see anything that has been going on like since 8 years ago, so it has been like this for quite some time. So when factoring out those new functions, those comments on the blocks that we have seen before are usually a very good indicator of how the functions could be named, right? Because the comments say what's going on in here, and the function name should say what's going on inside the function or what the function is doing. So with the 3 functions we have here on the lower side, well, the color comment is less expressive than the actual function name because it's update fill colors, not any colors. The next one, I think the comment is better readable than the name because text coords, I don't know whether everyone knows immediately what text coord is, but text coordinates, I think we can just use the longer function names because, well, screen real estate is not that costly anymore, so we can afford those few more characters, right? And, well, outline and update outline, the count just matches the function. So with a few keystrokes, we could just update this to this. And now we have like a higher level function. So the update of the shape is an update of the vertices, the fill colors, the texture coordinates, the outline. And how those are done in detail, we can see if we want to by jumping into the functions. Another example that we had before is the rectangle that makes up the left pedal, the right pedal, the ball. We can do basically the same here, factor out those functions. While I was at it, I also factored out those 2 colors that were used here because, well, if you look in this code, you have at least I have no good idea what the 100, 100, 200 and the 200, 100, 100 actually is about. This is another code smell, usually called like magic number or something like that. So actually factoring those out and giving them a more or less expressive name is something that we can also do. Probably I should have named it like pedal grayish dark blue or something like that because that's the actual color we have seen in the screenshot, but I think pedal blue and pedal red is enough, at least for slideware. So the thing is, when we factor out functions that are called create something, what's the first thing you think when a function creates something? How do we call those functions? Oh, those are constructed correctly. So instead of having a rectangle shape and a circle shape, we might as well just create actual classes that are called pedal and ball for this application, and we initialize them with the colors. So especially when we have like data and we have functionality that belongs to that data, it's only natural to actually bring this stuff together and make classes out of it, right? So When we see this code, there's something that, well, it's relatively symmetric, I would say. So we have like these three classes, and they get initialized with their respective colors. But by doing this, I sneaked in another code smell. I mean, how many balls do we have in the game? There's only one ball, right? So why do we need to parameterize the ball with an actual color? There's only the ball, and the ball is white in this game. If there were multiple balls and they could have different colors, that would be okay, but why do we need this as a constructor parameter? So this code smell is called premature generalization. So this is the usual what if. What if someone wants to use another ball or another color for the ball or multiple balls with different colors? You don't need it right now. So just don't use it. So the surface indication for, more generally, the premature generalization is we have needless parameters that only ever get one single value. We have, maybe it's not only function parameters, but maybe it's also configuration values that we have in our configuration files, some ini files that we use to configure our program, and there's only ever one value of this configuration value used. We never use this with another configuration value. Also in C++ templates that we only get instantiate with one single type. Why do we make a template out of it if it's not used? We have to put it in the header, unless we're using modules. We have to see the end, and it makes the compilation times worse, and so on. Also base classes that have only one derived class. Why do we need that base class if it's only one class? Unless we program against an interface, so we use the dependency inversion to actually only program against the interface and then have one instance of the derived class. But usually in that instance, in that use case, we don't have only one implementation, but we also use like mocks for unit tests that derive from the same interface. So then we already have like two derivatives of the same base class. So the problem here is we violate the keep it simple, stupid principle, and the you ain't gonna use it, you ain't gonna need it, so YAGNI. It makes the design usually more complex than it needs to be, and we probably are using programming language. We are programming because we are trying to solve complex problems, right? So we don't want to make them more complex than they already are. And we either have to use additional test cases. I mean, I'm pretty sure, and I hope that this would also work with a red ball or with a yellow ball or with a black ball. But being pretty sure and hoping doesn't mean that it actually works. So if I make the ball black or gray-black, you won't see it anymore on the screen. So I should probably add a test with a gray ball, and then, well, it's a usability, a visibility test. But still, I need to add those test cases for those additional possibilities that I've made, or I am lacking those test cases, which either way is not a good thing to have. So the simple fix is just keep it as simple as possible while still modeling the problem. So we just have a ball. And the fact that the ball is white is an implementation detail of the ball. Next snippet from that SFML example. We have the main game loop. While the window is open, we poll for events, and then we handle those events. And well, if there's no current game going on, so if we are not playing, then we have to set up a new game. We have to start a new game, and we have to basically generate an angle for the ball to start the game that is not like completely up or completely down, because that game would be unplayable, right? So there's a lot of things going on. And this code smell is called deeply nested control flow, where we have like different controls, for loops, while loops, ifs, maybe switch case statements nested inside each other. And so switch case is not on the slide here, but also try catch could also be seen as a control flow, and also like opening lambdas, which is like yet another level of indirection and yet another level we have to keep in mind, also goes into the direction of control flow. So basically, whenever we get an indentation and the indentation goes like right out of the screen, that's definitely too much, right? So what the problem, the underlying problem, it's just too much to keep in mind. How did we get there, and which conditions have you already checked, and which conditions did we do, didn't we do check, and so on and so forth. And again, well, to actually have those many levels of control flow, we usually have a relatively lengthy function. And again, in this case, we most often have violations of single responsibility or single level of abstraction or both. So the fix is more or less the same like for the long function. We factor out a function. We factor out the if block bodies or the while loop bodies to other functions, which in this case is basically, I factored this out, and you see basically if not is playing, then there was like I turned this the if condition around. So if you factor this out, then you get to this loop, which actually gets quite recognizable because that is an input update output loop or input processing output loop, which is something that we see in very many games, that we see very often in embedded applications and in other applications like as well, right? So this basic loop structure tells us anything we need to know about the actual loop, and then we can see what handling events does and what the update function does and what the output function does. So somewhere inside, I think it's what then would be the move entities part. So somewhere inside this big loop in the example, we have this beauty. And we have 2 or 3 or 4 of these. So if the position dot x, so the x coordinate of the position minus the ball radius is less than the left pedal, and so on and so forth. I won't bore you with the details right now because you will see them on the screen in a second. This is just a complicated expression. So there are catalogs out there that would say this is a complicated Boolean expression, but this goes for any expression, right? If you have like an arithmetic expression that calculates some numbers and it gets like 4, 5, 10 lines of code, it's also a complicated expression, which is not a good thing to have because this is on a very low detail level. And can anyone tell me what we are actually checking for here? No? Yeah, something inside bounds, right? So there is a helping comment above this thing. We check the collision between the ball and the pedals. So in this case, the left pedal. So the other instance of like similar 4 lines of code is for the right pedal, of course, which again is a violation of the single level of abstraction because we only want to check whether we have a collision and then we want to react to that collision. We don't want to check all those little details, right? So what we would like to have here is if the ball hits the left pedal, then we can do this kind of thing, or then we can do this and that reaction. Change the orientation of this, change the direction the ball is going into, and so on. So the fix for this is factoring out variables or functions with meaningful names. For example, the ball hits the left pedal. So how is this done? Well, the ball hits the left pedal if it touches the pedal and if it's more or less in the same height, right? So it doesn't, if it's above the pedal or below the pedal, it's not correct. So it has to be at the same height and touch the pedal, which in turn means it's above the lower edge and below the upper edge. And so we can factor out what is the actual meaning of the stuff we had here in the expression at first. And if you go to the length, then you have the upper edge, which is the position.y plus the ball radius and so on. And if you do this, then you see something that is quite odd here in the line ball touches pedal on the left, that has like the brake and the end condition. The ball touches the pedal when the left edge of the ball is smaller than the right edge of the pedal. It means it doesn't only touch the pedal, it already has like moved into the pedal. I don't know whether that is actually the way they wanted to do this. It's the way they did this. But if you look at these four lines we had in the beginning, you probably wouldn't see like this, that it's actually like finding a name for this variable, for this expression, said, well, it's actually not touching, it's actually moved into the pedal already. So maybe a bug, but the game is still playable, so probably doesn't matter too much. So since we already had the ball as a class and the pedal as a class, you can also like have these variables in the upper block is like ball something, ball something, ball something. So these are properties of the ball, and the next one are properties of the pedal. So you can just move them as member function into the ball, which makes the ball a higher level concept than the actual rectangle, and the pedal is a higher level concept than the rectangle, and the ball is a higher level concept than the actual circle shape we had in the beginning. And if you want to, since all these are details that probably don't belong into the logic part, you just factor this out into a separate function. Maybe the function needs a few parameters, but still, you factor those out into a function that has a meaningful name, and then it's out of the actual wave where you have like the high-level stuff going on. If the ball hits the pedal, I want to do this. If the ball hits the other pedal, I want to do something different. What I get relatively often is, that's a lot of code to write. I mean, you have seen like this was a complete slide of variables, right? But that's also a lot of that has been figured out. Someone has sat down to actually see, okay, what is the right height of the ball? What is how much to the left has the ball to be, more to the right than the center of the pedal, and so on and so forth. And to actually write this stuff out and giving the concept that you have in your mind names makes it more understandable for the next person who has to read this kind of thing, right? Because if you have to read like those 4 lines of code and trying to figure out, trying to actually, okay, what's going on here? Making notes, okay, this is the ball is touching the pedal on the left, and this is the ball on the right height, and so on. If you, as the first developers who write those kinds of code, give meaning to those variables and give names to those variables, then the next person actually reading the code doesn't have to figure it out all over again. The other argument that I get, this can't be good for performance, right? I mean, we are C++ people, so it's all about performance. The first question is, how do you know it's that problematic? The second question is, so it's a slight performance hit, does it actually matter? I mean, it's a game that goes with manual inputs, right? You don't have to like these super tight loops. And then we have very good optimizers. We have link time optimization, and I'm pretty sure if you take these functions, well, if you have them all in the same CPP file, and you tell the compiler, try to inline this, but usually the optimizer will go a long way to actually have the same expression in assembler or in the machine code that you had before, if you had like this huge if thing. So the important part is measure user profiler to actually tell you that this is a performance bottleneck, and the other thing is measure user profiler to actually tell you whether the complicated expression is more performance intensive than the fix where you made it more readable. So when talking about a profiler, who is regularly using a profiler, either in your CI builds or regularly manually using a profiler to actually profile your applications? Show of hands. 2 and 3 and 2.5 hands, more or less, I've seen. Okay. There's a smell that is not an actual code smell, but what I would call a build smell, not actually using tooling. that we have at hand. So if we care about performance so much, then we should use a profiler, of course. We also should use our compiler warnings to tell us about, well, not actual code smells, but code that actually may be problematic, right? We should use our optimizers, especially if we are going like on embedded, and I mean with embedded, I mean tiny embedded stuff and are performance bound or size bound. Then we should not try to squeeze our debug builds with debug information, everything on a tiny chip, because it doesn't need it in production, right? We should use static analysis tools. We should use sanitizers, UB sanitizers, address sanitizers, whatever you have. And use your IDE tooling, your refactoring tooling, because the stuff that I've shown you, getting from this big if condition to those lines of code with variables, with the correct tooling and knowing how to use the tooling, it takes like 2 minutes or 3 minutes, no more. Since we are with C++ now, let's talk about the C++ smell. So this is from libsas production code. SASS is basically used to create CSS style sheets. What's the problem here? So the right part on the right, the game width, pedal size, ball radius, I mean, it's the SFML example still, but the left side is from the SAS projects. We see a lot of getters here on the left side, a lot of query functions. And the code says that those query functions will modify the object they are working on. I mean, they don't, but the code says this because there's no const behind those getters. So this is the const-less smell. So if you see getters that don't have const, if you see actual constants that are declared to be constant by a comment that are not const, then there's something going on, right? So the problem behind that is that the semantics are not clear, because if you declare a function to be non-const and it looks like something that should be const, then probably someone will be at least hesitant to use it, because there might be some side effects they don't know about, because, well, if there are no side effect, why isn't it const? The other thing is we might accidentally modify variables that are meant to be const. If you mark them as const, the compiler will show us that this can't be done, or won't allow this. And we can't use those getters on constant variables. So the easiest fix will probably be to not make those variable constant. And then you get the same problem all over again, and it propagates to the code base, where you probably then have a code base that has little to no actual const variables, and you get all the problems that come with it. There is a talk that goes more in-depth into especially consts, but also other C++ code smells by Jason Turner from CppCon 2019, and I highly recommend to watch that talk. Next, C++ code smell. This is yet another open source code base, Ladder SDK. It's from an SD software development kit for some sensors and stuff like that, some library to deal with sensors. So this is not about the long function, even though I commented out 500 lines of code up here. This is about the C++ code smell that we see here. So lsensor2, lplayer are all pointers, plain C pointers. And at the end of this while loop, we have to look whether the pointer is not null, and then we have to disconnect the sensors, and then we have to delete the objects behind the pointer, and then we have to set the pointer to null, because directly after the while loop or after the try, we catch an exception and we have to go over the whole thing again, right? To disconnect stuff and delete stuff. We only don't have to null the pointers on the right hand side, because directly after the catch, the function is gone and the pointers are gone as well. So what's the problem here? Well, we should be using RAII. So this is a missing RAII. In this case, for these, at least for the deletion stuff, we should use a unique pointer, and maybe we should wrap this into something else that calls the disconnect, unless the destructor of the stuff calls the disconnect function anyway. I've tried to figure it out in the code base. It does something similar to the disconnect function, but there may be some side effects that are actually wanted. So we might want to have like a on scope exit or something like that that also actually calls disconnect on those sensors that we had in the code base here. And if we do this, use unique pointer and some RAII wrapper that automatically calls a disconnect, then this whole slide basically boils down to try while true, well, maybe not 500 lines of code if we factor them out, and then the single catch, and all the other stuff goes away because it's done automatically in the destructors of the unique pointer and of our scope wrapper. I think this is example code, but their production code looks like this as well. Well, it's more or less handled because they just write out the exception message and terminate the program, right? So, yeah, so probably catching exceptions in the production code is done a bit better, but like the handling with pointers, with raw C pointers and manually cleaning up stuff is done like this in the code base as well. Also in the same code base, but production code, there's a class letter can Komodo, which is a C++ wrapper around I think a C code base. Komodo seems to be a can library. There is this little thing, we have a destructor, and we have something that's called a handle. So probably the destructor is responsible for cleaning up the handle. That probably is something that has been opened, so they use RAII here. But the problem with this is this class is copyable and movable, and it doesn't care about the handle and about actually doing something with the handle. So if we copy this class, we have two objects of the same class with the same handle. The first one will close a handle in the destructor. The second one will close a handle in the destructor. It's not a delete, so it's not undefined behavior, maybe, but I don't know what the C library below does when you close the same handle twice, right? So if you look into the destructor, if there is a handle that is not 0, then it calls the disconnect on this class, and the disconnect function then checks again whether the handle is not null, and then uses disable the handle, close the handle. So this might be problematic if we close the same handle twice. So what's the actual smell here? Well, there is the rule of 5 in C++. When we write a destructor, copy constructor, or copy assignment, move constructor or move assignment, we should write them all. If the copy assignment, or if you have to implement the destructor and the other ones are okay as if they are done by the compiler, then we should still default them I mean, for the compiler, it's the same, right? It will generate the other ones, but for readers of the code, they see, okay, it's meant to be defaulted, and it's not left to chance whether we actually need the copy and whether the copy is done by accident. We are back to the SFML library. Windows implementation for joysticks. There's a loop about, so they have like a joystick list, and they loop over the records for this joystick list, and they try to find the record that has the correct index that we are given in here. And then we say, okay, if the record is in the list with the corresponding index, then this counts as connected, as it doesn't count as connected. And we have the same loop in several parts of the file. So it goes over the records, and this is also what was it? The smell with the indentations, the deeply nested control flow, because this function is not the only thing that happens, right? So like the 280 lines of code that I've commented out here contain other ifs and whiles and so on. So in this case, the smell that we have here are raw loops, or in this case, range for loops. 2.5 years ago, they were still raw loops, like iterator loops, because back then they were still using C++03, but still, range-based for means we are probably missing algorithms. So we should prefer range-based for over raw for loops. That's good, but we should prefer algorithms over for loops, because algorithms give names to the stuff we are doing here. So in this case, what is done here, like looping over the thing and finding the record that has the same index that we put into, is basically, well, I call it find by index. The algorithm in C++ is find if. So we let the algorithm find if something satisfies the predicate, which means that the record's index and the index I put into it are the same. And using this function, we can say that is connected input, the function we had before, just says, well, when find by index doesn't return the end iterator, then the thing is connected, which makes this one-liner. And the other thing is, well, the two nestings are gone away, because if we do go through the complete loop without finding anything, we were returning false, and this turns the stuff around, right? If we don't find anything, we return false first, so this is an early exit, and then we handle the thing if we actually found something. Sorry. Let's talk about loops a bit more and algorithms. So we have here some container with employees, and we want to convert this into a vector with employees. And the very naive way is just have a loop over the source container, and push a copy of every employee back into the vector, right? We can do better. We can use the statcopy algorithm to actually say we are copying all the stuff from here to there. Well, since we are pushing back into the vector, we need to use a back inserter, but still we say, okay, we push everything from here and insert it back into the vector. Or in this case, in this special case, we could just use the vector constructor that takes two iterators to actually copy the content of the iterator range we had before. Let's do something more complex. We have a map where we want to have the salaries by name of the employee. And the naive case again is we take a loop over our employees, over the vector we had, or over the original container, it doesn't matter. And we say, okay, the salaries by name, so in the map, the entry for the employee name is the employee salary. Pretty simple, right? Well, the smell says don't use raw loops or don't use range-based for loops if you can use an algorithm. So what's the algorithm for this one? So instead of just using the bracket thing, we could also use emplace, which is, well, tiny bit more performant, but we could try to use it if the performance is a thing here. I think it's a bit less readable than the one before, but it also is a matter of taste, right? So, but still, what's the algorithm we have to use here? Any ideas? Transform. So the transform for this is we transform from stat begin to stat end of the employees. We need to have an inserter into the map, but an inserter also needs a hint iterator. So I need the end iterator. I take the end iterator of the map. I could also use the begin iterator of the map. It doesn't really matter because in most cases it will be the wrong iterator, the hint. And then I have to the transformation function is the lambda that takes an employee and returns a pair of the unique name and the salary. I think the loop is a bit more readable, right? Great. It goes on. We want the salaries by name, but not for managers, because, well, managers, they don't really want their salaries out there, right? What's the name for the algorithm here? Sorry? I didn't get. Filter. It's part of it, yes. So the standard algorithm for iterators would be named transform if that one existed. It doesn't. So if you have something that does something, but with a predicate, with a filter predicate, it's usually written with underscore if in the end, like write copy and copy if, or remove and remove if, and so on. So this would be transform if. So if we look into the standard library, for example, how copy if and transform are written, we can piece together how transform if would look like. That's on the left side. And on the right side, we have the implementation of our for loop with the if condition to actually use transform if, begin, and again, the complicated inserter. And then at first, we have the transformation function, and then we have the predicate for the if. That doesn't really look readable, right? So, well, since we have C++ 20 or are close to 23 now, how about ranges? So I take the employees, I pass them through a filter with a predicate, I pass those to a transform that creates a pairs, and then I pass this to a generator that generates a map for me. Definitely looks more readable than the invocation of transform if we had before, but I would still say that the for loop we had in the beginning is way more readable than that. And by the way, std ranges to std map is something that comes, I think, with 26. No, it comes with 23. So we still don't have that right. So back to the for loops. The range for, instead of using the algorithm, is still a smell, which is an indication that usually, but not in this case, shows a deeper problem. So in this case, it doesn't need fixing. We still should use the for loop because it's more readable, and this is what matters in this case. And it's also more performant than having always like the inserter using the wrong insertion hint and copying the pair and then having to transform the pair into another pair, because the pair we made here with make pair has a non-const first element, and map pairs, the elements of a map, have a const. So we could have done better by still writing more code and making explicit that this is a pair of const string to unsigned, and it's just not worth it. So what we've talked about. Sorry. You've seen the long functions, premature generalization, magic number or magic color in this case on the side. We had the deeply nested control flows and the complicated expressions. Those were more general code smells. Those are not C++ specific, right? You have the same code smells in Java, in Python, in any language. Then we had a few C++ smells, const expression less code or const less code, code that is missing RAII, code that is missing the rule of 5, or even better, the rule of 0, and the raw loops or the range for loops, so missing algorithms. For the first algorithm, for the first smells, I have this link down here, sourcemaking.com, about it contains a list of smells. I think it's about 30, 40 smells that are there. Not all apply equally importantly to C++, because there are some smells that I would say are more into the direction of Java, C#, where you have like these purely object-oriented thinking, which doesn't always apply for C++. But still there are a few learnings that you can have in there. So code smells can be found in any code base. I bet in your code base as well. These examples are not necessarily bad code. Some are worse than others. Some we could say, okay, just leave them like this. It's not that bad. But seeing them, knowing them, okay, this is a long function, I should look into this, whether there is a problem. And maybe I should leave a comment above this or a comment above the for loop. I try to use transform if, but please don't try because it just looks horrible, is something that we can do. And in this case, even though the SFML is reduced to C++ 11 or 14, I think right now, that does not mean we cannot write cleaner code, right? So a few talks that I can recommend: the Jason Turner talk from CppCon 2019 about code smells, C++ code smells. I already mentioned that on the one slide. Same conference by Kate Gregory, Naming is Hard, Let's Do Better. And just recently, I think the video is out already from ACCUConf 2022, so just a few months ago, a few weeks ago, the abstraction patterns by Kate Gregory. I definitely can recommend that to actually make code more readable without actually having the deep understanding you maybe need. That's from me. Thank you very much. Are there questions?